Another episode in the Mathematics of Juggling video series. Here we're going to be looking at juggling cards. Juggling cards are used to create juggling graphs, which we've seen represent the siteswaps we've been studying. In fact, here's a familiar siteswap and juggling graph. 7562 is a 5-ball siteswap. I want to focus on two edges here and the relationship between them. Here I have a red edge and a green edge. Let's look at their endpoints. The red edge has a left endpoint at beat 2 and a right endpoint at beat 8. This makes sense because the red edge represents a throw of height 6. 2, the left endpoint, plus 6 is equal to 8. On the other hand, the green edge starts at beat 4 and ends at beat 11. It represents a throw of height 7. 4 plus 7 is equal to 11. Notice that the left endpoint of the green edge is between the endpoints of the red edge. That is, 4 is between 2 and 8. The right endpoint of the green edge, beat 11, is to the right of the right endpoint of the red edge, beat 8. When this occurs, those two edges must intersect, they must cross, so we call this a crossing. From a juggling perspective, a crossing occurs when we throw two balls so that the second ball is thrown before the first ball lands, and the second ball lands after the first ball does. It turns out that there are three other edges that form a crossing with the red edge. That is, there are three other edges whose left endpoint is between beats 2 and beat 8, and whose right endpoint is after beat 8. Do you see where they are? Turns out they're at beats 5, they start at beat 5, or beat 6, or beat 7. There are 4 crossings for this particular red edge. Richard Ehrenborg and Margaret Reedy, in their paper Juggling and Applications to Q Analogs, said that we should probably draw the graphs so that the crossings occur just before the vertices, just before the beats. What this is going to do is it's going to provide a uniformity. So I'm going to take the juggling graph 7562 and draw it in this fashion, but I'm going to extract it from well into the pattern so that all the balls are already in the air. I said it establishes some uniformity. What I'm going to do is I'm going to put some dotted lines in here halfway between consecutive vertices. And let's observe that there are some regions that, even though they represent different parts of the juggling graph, will look the same. For example, let's look at these two regions. The left one, we're about to execute a throw of height 7, but it looks the same as the right one, which is where we're about to execute a throw of height 2. The reason they look the same is because they both have 4 crossings. On the other hand, in this region, there are only 3 crossings, and in this region, there's 1. We could have 2 crossings, or we could have 0 crossings. 0 crossings can occur in one of 2 ways. But these are the only possibilities, which means we have a finite number of options for how the graph will look between 2 consecutive dotted lines. And so we can make a deck of juggling cards. At the very right of these juggling cards, you see we have 4 crossings. To the left of that, we have 3, and then 2, and then 1. The left 2 cards have 0 crossings. Now, the first one is special because it corresponds to a throw of height 0, and we call that a no throw. Now, 7562, as we explained, is a 5-ball siteswap, which means there are kind of like 5 paths that move across this graph. The maximum number of crossings we can have is 4 because the top line, the top path, can cross the other 4. Because the maximum number of balls we can be juggling when forming a list of these juggling cards is 5, we'll call this the deck D sub 5, and it has 6 cards. Ehrenborg and Reedy also established the fact that there's a 1-to-1 correspondence between siteswaps of period n with b or fewer balls and sequences of n juggling cards from the deck D sub b. By a 1-to-1 correspondence, it means we can pair up siteswaps with sequences of juggling cards one at a time. Here I have a sequence of 5 juggling cards from the deck D sub 5. So n is equal to 5 because there are 5 cards. B is equal to 5 because there are 5 paths moving across here. So let's ask this question. What period 5 siteswap corresponds to this sequence of juggling cards? And how many balls are we juggling? Recreating the siteswap is pretty straightforward. All we have to do is start at a vertex, figure out how long that ball's in the air. This one in particular is in the air for 2 beats, so the first throw is a throw of height 2. The second one, well, we have a little bit of a problem because we just passed 3 vertices and we ended up at the end of the card. We could recopy these 5 cards and continue from there, or note that this is on the middle rung on the very right, right? There are 5 paths going up. It's on the third one up, so let's start at the third one up there. Now, we said we already passed 3 vertices. There's the fourth, and we land at the fifth. Another way you can convince yourself this is a throw of height 5 is because we started at this particular card, we ended at this particular card. There are 5 cards, so it's a throw of height 5. For the next one, we move along, we pass 2 vertices. We're at the second rung from the bottom. Now we start at the second rung from the bottom on the left, and we'll pass 5 more vertices. 2 on the first pass, 5 on the second will make 7 total. We're at the second from the top, and we're going to land at beat 8. So that's a throw of height 8. The next throw is very simple. We don't have anything coming down, so that's a no throw. That corresponds to a throw of height 0. And the last one, we start off and we're at the very bottom. We haven't passed any vertices yet. And suddenly we go 1, 2, 3, 4, 5. It started and ended at the same place. So that's another throw of height 5. To find the number of balls, all we have to do is use the average theorem. The average of 2, 5, 8, 0, and 5 is 4, and so this is a 4-ball siteswap. Now that seems kind of strange. We were dealing from the deck D sub 5, but it's only a 4-ball siteswap. Why is it only 4? Well, let's look at the top rung. We never really encountered that. If you follow that, you're just going to end up on that one all the time. It's as if there's this ball suspended in midair that the juggler never gets to catch. So it's really only a 4-ball siteswap. Now we've just taken sequences of juggling cards and recreated a siteswap. How do you go the other way? To go the other way, first of all, we need to determine B, how many balls are we juggling? That's going to help us know what deck or decks we can choose from. Then draw the juggling graph. And then we go back to the little crossing idea. Treat each beat like the right end point of a red edge, and then how many green edges will cross that red one. We'll do an example to help illustrate that. You count the number of crossings, find the corresponding card from the deck that you've chosen. Now, if I'm working with a siteswap for a 7-ball siteswap, I can choose cards from deck D7 or D8 or D9 or D10. Anything where the number of balls is 7 or more. I can't choose cards from the deck D5 if I have a 7-ball siteswap. You also want to watch out for that no-throw card. If you have a throw of height 0, you want to put in the no-throw card. We're going to look at an example that we've played with before, 5-7-2-4-7, 5-7-2-4-7. Now we need to go far enough into the graph so that all the balls are in the air. It turns out we need to make our way to the third period before that happens. So what we do is we focus on the edge coming in at beat 10, and we see how many crossings there are. Well, there are 3 crossings in this particular instance. So we're going to pull the card with 3 crossings. I'm just going to go ahead and use the deck D sub 5 because this is a 5-ball siteswap. For the next one, how many crossings are there? Well, there are 4 this time. 2 of them in the middle are a little bit harder to see, but there are 2 there. So we're going to put the 4 crossing card next. And then this one I'm going to pause for a moment. Notice this corresponds to a throw of height 4. That means there are only 3 vertices between the left endpoint and the right endpoint, so the maximum number of crossings we can have is actually 3. And it turns out in this case we do get all 3. The next one is the ball landing at beat 13. How many edges cross that? Well, we've got 4 crossing there. And then the last one, landing at beat 14, how many edges cross there? Well, it corresponds to a throw of height 2, so the maximum number we could have would be 1, and in fact we do get 1. Now if you really want to verify that this is the siteswap 5-7-2-4-7, you can slide these cards over and then make more copies of them, and then count to make sure that it is indeed 5-7-2-4-7. So where do we go from here? Well, we're going to do some counting. The question is, what are we going to be counting? Do we want to count 7-5-6-2 and 2-7-5-6 as distinct period 4 siteswaps? Well, why would we count them as the same? If you take the 2 from the back end of 7562 and move it to the front, you get 2756. So from a juggling perspective, they really kind of are the same. Sometimes we'll count them as different site swaps. Sometimes we'll count them as the same or equivalent. How about 9191? Do we want to count it as a period 4 site swap, or really we could just do the 91, which is a period 2 site swap? Again, sometimes we'll count it as a 4-ball site swap or a period 4 site swap. Sometimes we'll count it as a period 2 site swap. In the next video, what we're going to do is we're going to end up being able to count things like how many 5-ball site swaps are there of period 4? Or more generally, how many B-ball site swaps are there of period N?